Another simple type of differential equation to solve is linear differential equations. Now you already have practice identifying these. So today we'll review what they look like and then we'll talk about the process of solving them. Now, just to refresh your memory, a linear differential equation is one that can be written in the form a sub 1 of x, some function of x, times the derivative of y with respect to x, plus some a sub 0 function of x times y equals g of x, which is just a function in x. Now, to make this look a little bit more like our normal form of a differential equation, we want to solve it for dy dx. So we'll take a step towards doing that by dividing all of the terms by our function a1 of x. So when we divide all of our terms by a1 of x, we're left with dy dx plus a0 of x divided by a1 of x times y equals g of x divided by a1 of x. Now notice a sub 0 of x divided by a1 of x, that's just another function of x. So we can write it as p of x. And g of x divided by a1 of x is also just a function of x, so we'll write it f of x. When we do that, we get the standard form of a linear differential equation. That is dy dx plus p of x times y equals f of x. Now, let's step to the side for a minute and remember from Calculus 1 that if we take the derivative of a product, say of some function mu of x and y, the derivative of that product is mu of x times dy dx plus d mu dx times y. So now I'm going to apply that, and I'm going to get lazy about writing the of x part on things, but let's take a look at the left-hand side of our standard form, the dy dx plus p of x times y part. If I multiply that side by mu of x, because I could multiply the entire standard form by mu of x if I wanted to, so let's say I do, I get mu of x dy dx plus mu of x times p of x times y. Well, that looks a lot like the results of taking the derivative of a product when we use the product rule. So I've rewritten the result when we take the product rule of mu of x times y, and that product was the mu of x times dy dx plus d mu dx times y. Now, I've put these equal to each other because they look so similar. And in fact, they would be exactly equal to each other if only mu of x times p of x equaled the derivative of mu with respect to x. So what I have here is a differential equation that if it's true, then my left-hand side when I multiply times mu of x is just the derivative of a product. So let's try to solve that differential equation and see if it has a solution. So when I solve that differential equation, I'm going to use separation of variables. So I will multiply by dx and divide by mu, leaving me with p dx equals d mu divided by mu. Integrating both sides, I get the integral of p of x dx is going to equal the natural log of the absolute value of mu plus some constant. So that means that mu is going to equal e to the integral of p of x dx plus some constant, which remember is a constant times e to the integral of p of x dx. Since this is true for any value that constant can take on, we're going to choose 1 as that constant value just to make it easy So mu of x is going to equal e to the integral of p of x dx. Now mu of x equals e to the integral of p of x dx is so special it gets a name. It's called the integrating factor, or n integrating factor. And we're going to use that to solve linear first order differential equations. So if you're looking to solve a linear first order differential equation, you don't need to go through all of those steps to find the integrating factor, unless you've forgotten what it is, in which case you might need to recreate it. But if you just remember this integrating factor, you'll be able to use it and follow these steps. The first is to put the linear equation into standard form. Then, from your standard form, you're going to be able to identify some function of x, p of x, that is, that specific coefficient on y. And you're going to use it to find the integrating factor. So you'll plug it in, you'll take this integral of p of x dx, and that will be the exponent on your e value. Now, when you take this integral, it's an indefinite integral, so pretty much every other place that you would be taking this integral, you would have to add a constant. This is the one place where you're not going to have to do that. So when you take this integral, you won't have to add that constant, because again, we would basically just assume it away to be 1, and so we can just not do it in this one case. All right. So once we've found our integrating factor, we're going to multiply both sides of the standard form of our linear first order differential equation by the integrating factor. When we do that, the left-hand side is automatically going to be set up to be the derivative of the product of the integrating factor and y. So that means that our differential equation is going to end up looking like the derivative of the quantity e to the integral of p of x dx times y. And I encourage you to leave it in that form on the left-hand side. And it's going to equal e to the integral of p of x dx times f of x on the right-hand side. Now, we're going to be able to integrate both sides and solve for y. Now, why I encourage you to leave it that way on the left-hand side as just the derivative of that product without actually taking the derivative is when we go to integrate, we're going to be integrating a derivative, and so we'll save ourselves a lot of trouble by just not taking that derivative of that product. So now that we've talked through the steps for solving a linear first order equation, let's go through an example or two so you see how this works. So the first example we're going to look at is dy dx minus 3y equals 6. Now this is already in standard form, so we've done the first step. Our second step is to identify p of x and use it to find the integrating factor. Now remember, p of x is the coefficient on y. So our p of x value is going to be -3, because this would be plus p of xy. So we have p of x equals -3. So we've identified p of x, so the next thing is to use it to find the integrating factor. So we'll be finding our integrating factor. Mu of x is going to equal e to the integral of -3 dx. Now, the integral of -3 dx is just -3x, so this is going to equal e to the -3x power, and remember, we don't have to put the plus c there. So now we're going to move on to the multiply both sides of the standard form by the integrating factor. So we're going to have e to the -3x dy dx minus 3 e to the -3xy equals 6e to the negative 3x. Now, when you do that, notice this is the product rule worked out. So I'm going to simplify it back to the derivative form that we saw in step 3. So this is really d dx of e to the negative 3x y. And it's going to equal 6e to the negative 3x. So now all that's left is for us to integrate both sides so we can solve for y. So integrating both sides, we have an integral of a derivative, so those cancel each other out. So we have e to the negative 3x y on the left-hand side. And on the right-hand side, we'll be taking the integral of 6e to the negative 3x dx. And that will give us negative 6e to the negative 3x divided by 3 plus a constant. And now we just have to solve for y. We've done the integrating part. So solving for y is as simple as dividing by e to the negative 3x. So in this first term on the right-hand side, negative 6 divided by 3 is going to be negative 2, so that's already simplified down for us. And then e to the negative 3x divided by e to the negative 3x will be 1, so we don't even have to write that part. And then we're going to add c divided by e to the negative 3x. Now, dividing by e to the negative 3x is the same as multiplying by e to the 3x. So we can also rewrite this in a little bit nicer form by writing it as negative 2 plus ce to the 3x power. Remember, taking the negative in an exponent just moves it back and forth between the numerator and denominator. And this is the solution to our linear differential equation. Now, the same way that we could have initial value problems when we had separable equations, we can also have initial value problems with linear differential equations. So let's take a look at an example with an initial value problem. So we'll have dy dx plus y equals x, and we have y of 0 equals 4. So now, just like we did with separable equations, when we have an initial value problem, we still go through and solve the differential equation and then use the initial value to find what the specific value for that constant is to find the particular solution from the family of solutions that we find. So we need this in standard form. Luckily, it's already there. And then we need to identify p of x. Well, p of x is the coefficient function of x on y. In this case, it's just 1. So p of x equals 1. And we need to use that to find our integrating factor. So we have mu of x is going to equal e to the integral of 1 dx. The integral of 1 dx is just x, so this will just be e to the x. So now we need to multiply our entire function by e to the x. So we'll have e to the x dy dx plus y e to the x equals x e to the x. Now again, I can rewrite this as d dx of e to the x y, and it's going to equal my right-hand side unchanged, x e to the x. And then I'll want to integrate both sides. So taking my integral, I have e to the xy equals, and integrating my right-hand side, I'm going to want to do a quick little integration by parts to do this, where I have a u value of x and a dv value of e to the x. And when I do that, what I'm going to end up with is and x e to the x minus e to the x plus some constant. And all that's left for me to do is solve for y. Solving for y is as simple as dividing by e to the x, so I get y equals x e to the x divided by e to the x is just x, minus e to the x divided by e to the x is 1, plus a constant divided by e to the x. Now again, I have a positive exponent in the denominator, so you could bring that up and make it a negative exponent. That's kind of a what do you want to do? It's up to you, preference thing. But what we really need to do is solve for our constant. So let's go back and use our initial condition we're given. We're given y of 0 equals 4. So I'll be substituting in 4 for y and 0 for x. Now, e to the 0 power is just 1. Anything to the 0 is 1. So I have c divided by 1, or just c. So I have 4 equals minus 1 plus c. So I add 1 to both sides, I get 5 equals c. So my particular solution then is y equals x minus 1 plus 5e to the negative x, or 5 divided by e to the positive x, whichever you prefer.